Hello, everyone. Today we're going to talk about what are called antiderivatives. So our definition, a function, capital F, so this is important, capital F is an antiderivative of F on an interval I if the derivative of big F prime is equal to f of x. And this is for all x in the interval. So let's look at some examples. So if we have, let's say, 2x cosine x and 1 over x plus 2e to the 2x. Right. So now I have this f prime of x. I already know the derivative. So we can think about this. So these are all our derivatives. We want to figure out what the starting function should be. So we think for 2x, what has the derivative x squared? Sorry, 2x, and that would be x squared. Right? What about cosine x? If cosine x is the derivative, the function would be sine x. If we have 1 over x, that'd be ln absolute value of x. And then 2e to the 2x, that's a little tricky, because we would have used the chain rule. So it'd be e to the 2x. So we're thinking about it backwards, because we know x squared goes to 2x, sine x goes to cosine x, and so on. Now we're working backwards. What if I have the derivative? What would the original function be? So from here, I'm going to give you a theorem. If f is an antiderivative of f on I, then the most general antiderivative of f on I is f of x plus c, where c is an arbitrary constant. So an arbitrary constant, all right? So let's look at an example. So I'm going to go more specific and then more in general. So let's say I want to find the antiderivative of f of x equals 3x squared. That satisfies f of 1 equals minus 1. Okay, so let's figure this out. So let's think of what we know. So if small f of x is 3x squared, what would have been my original function? What would be my big F? So what has the derivative? 3x squared. And we know that's x to the third. So our big F, so our original function, would have been x to the third. So we're just thinking about working backwards now. But then our theorem tells us we need to add plus c. So this is important. We're always going to add this arbitrary constant. In this case, we can even figure out what the c would be. Okay? So we know that f of 1 is negative 1. So f of 1 equals 1 to the third plus c. So if we simplify this, f of 1 we know is negative 1. 1 to the third plus c. This is 1 plus c. So now we know c is negative 2. Right? So our original f of x would be x to the third minus 2. Because we know if we take the derivative of negative 2, it's 0. So that's why we add this plus c. Because there could be some constant there, because when we take the derivative, it's 0, so it just goes away. So there's a lot of things that have 3x squared as their derivative, because they could just add or subtract any constant, and it still has the derivative 3x squared. So when we work backwards, we account for that by adding plus c. So let's do some examples in general. I'm going to give you small f of x. I want you to find big f of x. Let's do x to the fifth. 1 over root x. Sine 2x. Cosine x over 2. And f of x. E to the negative 3x. And f of x is 2 to the x. Okay. So let's go one by one. So if I have x to the fifth, I know that the derivative to be x to the fifth, the original power would have had to be x to the sixth. Okay. So my big f of x would have had to be x to the sixth, but when I move that 6 to the front, I would have had 6x to the fifth. So to compensate for that, I'll divide by 6. Okay? So if I take the derivative of 1/6 x to the 6th, I move the 6 to the front, the 6's go away, I subtract 1 from the power, and I get x to the fifth. And we'll soon see that this is a rule, that we're adding 1 to the power and then dividing by that number when we find the antiderivative. We can kind of use that thought process here. If I have 1 over root x, or x to the negative 1/2, the original power would have had to be x to the 1/2. But again, we have to compensate for that when we move the number to the front with the power rule. So this would be 2 root x plus c. Right? This next one's a little bit easier. So if I have sine 2x, since we're going to use the chain rule when we take the derivative, I would have needed a minus 1/2 and then cosine 2x. So again, the derivative of cosine is sine. Sorry, minus cosine is sine. But then since it's 2x and we didn't have a number in front of the sign, we would have to know that we needed 1/2 there because the chain rule would bring a 2 to the front. So 2 and the 1/2 would cancel out, and then we'd be correct. And then, of course, we cannot forget plus c. And the next one's actually the same problem almost. We know that the antiderivative of cosine would then have to be sine from the last one, x over 2 plus c. Originally, we would have had to use the chain rule to deal with this 1 over 2. X over 2 is the same thing as 1/2 x. So this time, I would need a 2 out in front. And then if I take the derivative of 2 sine x over 2, I'd get cosine x over 2. So a good way to check is take the derivative of the new function that you find. And if it's correct, then you found the antiderivative. And then soon we'll learn some rules. For right now, we're trying to figure it out from trying to work backwards. So again, I would need to think about the chain rule here. So I'd have minus 1/3 e to the negative 3x. And then the last one, if I get 2 to the x, I would have had to start with 1 over ln 2, 2 to the x plus c. Sounds a little trickier there. But soon we will learn some rules. Let me give you a definition. We say the collection of all antiderivatives of f is called the indefinite integral of f with respect to x. We write it as the integral of f of x dx. So we want to integrate something like x squared minus 2x plus 5 dx. We take it term by term. The antiderivative of x squared is going to be x to the third over 3. Because if I take the derivative of x to the third over 3, I get x squared. So that makes minus 2x minus x squared. And 5 would be plus 5x. And then plus c. That's how we take an integral. So to make this a little bit easier now, I'm going to give you a bunch of formulas so you don't have to guess and check all of these. So these formulas are ones you're going to want to know and probably have most of them memorized. Maybe not all of them. So if I have the integral of x to the n, this is the same thing as x to the n plus 1 over n plus 1 plus c. So it's similar to a derivative, but now we're adding 1. Sine x be minus cosine x plus c. Cosine x would now be sine x plus c. Secant squared. So we can only do secant squared because we know that goes, the derivative of tangent is secant squared. The integral of secant is actually a much harder problem. That's more for Calc 2. Cosecant squared x be minus cotangent x plus c. If I do secant x tan x, that would give us secant x plus c. If I do cosecant x cotangent x, I'd have minus cosecant x plus c. All right, so those are all of our trig ones there. Easiest one is e to the x. It's still e to the x plus c. If I have 1 over x dx, that goes to ln. If I have 1 over root 1 minus x squared, this would give me arc sine x plus c. We won't use these very much, but I'm going to give them to you. Can't forget the dx. If we have 1 over root 1 minus x squared, so the other way around dx, this would give me arc cosine x plus c. If I have 1 over 1 plus x squared dx, that's going to give me arc tangent. And then lastly, if I have 1 over x root x squared minus 1, then we'll get arc secant x plus c, and x has to be bigger than 1. And then one last one should help with the one we just did. If I have a to the x dx equals a over x ln a plus c. Sometimes it's 1 over ln a times a to the x, but it means the same things. So I'm going to have you practice some problems using these properties. And that will be it for today. I hope everyone has a great day, and I will see you next class.